So we're jumping into chapter 6. All right, so let's talk about some terminology first. A differential equation is just an equation involving a function and its derivatives. That's all we mean by differential equation. You may also run into integral equations, so equations that involve a function and its integrals. And we know how to solve some differential equations. For example, dy dx equals x squared. There's an equation that involves a function and its derivative. How would we solve this? You just basically you multiply by dx, you integrate both sides. That's that one way to solve a differential equation. So we know a little bit about differential equations, one type of differential equation already. First order just means that the highest derivative that you see in the equation is the first derivative. And linear just means the function and its derivatives only appear to the first power. All right, so our first order linear differential equation has the form dy dx plus p of x y, some function of x times y plus, equals q of x. Or often you will see differential equations written this way. Y prime plus p of x y equals q of x. We use the prime notation instead of dy dx. But these two are equivalent. And p and q are just continuous functions of x. We call this standard form. Once we get a first order linear differential equation into standard form, the solution method is relatively straightforward. So what I want to do is show you the solution method. There's an algorithm for coming up with the solution to this differential equation. So I want to show you the algorithm, show you the formula, and then I want to show you why the formula works. I'm a big one for not memorizing formulas, but understanding how the thing works. Because if you understand how it works, then you know more about it than if you plug into a formula. All right, to solve, we find what we call an integrating factor. So solving these involves evaluating integrals. And our integrating factor, often with differential equations, the way that we've come up with solutions is mathematicians said, well, I think if I do this and this and this, this is going to solve this kind of equation. So it's kind of, they come up with a solution not analytically, but empirically. They come up with a function and they say, see, this function satisfies this differential equation. So I haven't been able to find out who came up with the idea of an integrating factor, but I think from what I understand about differential equations, probably someone said, well, this thing solves a differential equation, and just came up with a solution. Our integrating factor, u of x, is e to the integral of p of x dx. So this is our integrating factor. So this p of x is what shows up inside our integral. And then our solution, is everybody good with our integrating factor? Write it in standard form. It needs to be in standard form so we can figure out what p of x is. And then our general solution we can write as y equals 1 over u of x, the integral of q of x times u of x dx. So we evaluate another integral to solve our equation. So that's our formula. That's the solution to this first order linear differential equation, where u of x is e to the integral of p of x dx. So I want to do an example where we use this formula, and then I want to do an example where I show you why this formula works. All right, so questions so far? And often, I took a graduate level partial differential equations course, and the solutions are often presented this. This is a solution to this kind of differential equation. Not necessarily deriving here is a proof that or here's how we come up with the solution, but here's a solution. We just figured out that this works. All right, so let's look at an example. So we want to solve y prime minus 3y equals e to the 2x. All right, so first order linear differential equation, first derivative, there's my function. We have continuous functions of x here. So I have p of x, this coefficient on the y term on the function is -3, and q of x is e to the 2x. So we need to find our integrating factor. U of x is e to the integral of -3 dx. And what does this give us? Integral of -3 dx is -3x, so we get e to the -3x. For the integrating factor, you do not need to include the plus c, because it turns out that when the constant of integration ends up going away if you go through the you see that it goes away if you go through the process of including it. Yeah. Oh, u of x, yes. I just forgot to put our variable there. All right, so the solution. Just plugging into our formula, y equals 1 over e to the -3x. There's our 1 over our u of x. The integral of e to the 2x times e to the -3x dx. So I'm just going to note here, this is 1 over u of x. This is q of x, and this is u of x. I'm just plugging into that formula. Well, this turns into a nice integral, so we get y equals, I'm going to rewrite this as e to the 3x times either the 2x times e to the minus 3x is just the integral of e to the minus x dx. And you have to be careful here. So be very careful when you do this integral. You do need the constant of integration on the second integral, on this integral, but notice it's being multiplied by this 1 over u of x. So this is e to the 3x times integral of e to the minus x plus c. The constant of integration gets multiplied by this. That's important in your solution. So the solution to that differential equation, the general solution, y equals, when I multiply this, minus e to the 2x plus c e to the 3x. That's my general solution. This constant of integration then would be determined by some initial condition on your differential equation. When x equals 0, y equals something. And that would give you your constant of integration. Yeah?
Is it okay if we don't multiply the e to the 3x out?
If you just left it like this,
Yeah.
that would be fine. But what students often do is leave this c, they just multiply these two, and leave the c sitting out just a plus c. But then your solution is off by a factor of e to the 3x, which, and depending on your function and how it comes out, that turns out to be a big deal. And if you plug this back in to this equation, take the derivative of this function, subtract 3 times this function, it would equal e to the 2x. That's what that differential equation tells us. So an example of where differential equations might come up is if you talk about an object falling with air resistance. So often air resistance is going to depend on the speed of the object. So its position is a function of the gravity and some factor that has to do with the speed of the object. So that would be an example of where a differential equation might come up in application. So you have an equation that has to do with a function and its derivative. Function is the particle's position, and the derivative is its speed, and the force, the frictional force is dependent on the speed. Sometimes it makes sense to model the frictional force on the square of the speed, and then you get a more complicated differential equation. So different ways they come up. All right, so questions on using that formula to find your general solution of that differential equation. All right, let's take a look at why this works. And then we'll do an example following along and applying the ideas of why it works. All right, so we're starting with y prime plus p of x y equals q of x. That's our first order linear differential equation. Our integrating factor. U of x is e to the integral of p of x dx. Now what we do with this integrating factor, I'm going to multiply the entire equation by the integrating factor. And that's why we call it in the end, that's why we call it the integrating factor. So I'm going to say y prime e to the integral of p of x dx plus p of x y e to the integral p of x dx equals q of x times e to the integral of p of x dx. All right, let's look at this quantity. What's the derivative of e to the integral of p of x dx? So we're going to do, we need the chain rule, right? So what's it going to be? What's the derivative of e to the something? E to the something, e to the p of x dx times p of x. Well, here's e to the something times p of x. So and here is y prime and times that thing. What does that look like? Where do you have the derivative of something times something else plus something else times the derivative of something? Isn't that the product rule?
Yeah.
This is the derivative of a product. So that integrating factor turns the left-hand side of our differential equation into the derivative of a product. So I can rewrite that as y e to the integral of p of x dx quantity prime, because if I take the derivative of this, I get this whole thing, right? Using the product rule, equals, and this is a prime, not a 1, prime, equals q of x e to the integral of p of x dx. Well, how do we solve a differential equation where we have a derivative on one side and just some function of x on the other side? Don't we just integrate both sides? Just like we had dy equals x squared dx. Integrate both sides. So when we integrate this derivative, what happens to the derivative? It just, when you take the integral of a derivative, we just get the thing, right? So we get y e to the integral of p of x dx equals the integral of q of x e to the integral of p of x dx dx. An integral inside an integral. That's interesting. And now I divide both sides by e to the integral of p of x dx, and I get y equals 1 over u of x, the integral q of x, u of x dx. Because e to the integral of p of x dx is just u of x. So we get back to our formula. So multiplying both sides of the equation by that integrating factor turns the left-hand side into the derivative of a product. That's why it works. And if you recognize that, I think that you understand more what's going on with the solution method than plugging into the formula. All right, so let's look at an example where we apply this kind of idea. When I do these first-order linear differential equations, I always multiply through by the integrating factor and do it this way. Because I have a hard time memorizing formulas, and I don't like to memorize formulas. I'd rather know how it works. All right, so questions on that process. So that's why it works. We turn the left-hand side into the derivative of a product. All right. So we're going to solve x squared y prime plus 5xy plus 3x to the fifth equals 0. This is a y prime, yes. All right, so this is kind of a complicated differential equation. It says if we multiply the derivative of a function by x squared, add it to the function times 5x, add 3x to the fifth, that equals 0. So it's kind of an interesting relationship. All right, what do we need to do first here? We need to get it in standard form, right? In standard form, the coefficient on y prime is 1. And we need to have q of x here on the right-hand side. So standard form is going to be y prime. I'm going to divide everything by x squared plus 5 over x. Y equals, and get this over onto the other side, and I get minus 3x to the third. There we have standard form. So my p of x, coefficient on y, is 5 over x. My q of x is minus 3x to the third. And my integrating factor, u of x, is going to be e to the integral of 5 over x dx. All right, so what do we get here when we integrate e to the 5 over x dx? So we get e to the 5 natural log absolute value of x. And here's something to pay attention to, because this happens kind of not it's not unusual for this to happen. I don't want this e to the something. How can I rewrite that to make it look nicer? What can we do with this this factor on a natural log function? It turns it into an exponent. So this is e to the natural log of x to the fifth, which is just absolute value. So u of x equals absolute value of x to the fifth. Now, I'm going to say we can drop the absolute value. So why could we drop the absolute value? If x is positive, it doesn't matter, right? If x is negative, what are we going to do with this u of x in this technique, not plugging into the formula with the technique that I talked about before? We're going to multiply everything by u of x. Well, if u of x is negative, we're multiplying every term in our differential equation by a negative, if x is negative. And what happens to those negatives? Can't we just divide or multiply by -1 and then they go away and they're the same thing? So since we're multiplying everything by this quantity, it doesn't matter if it's positive or negative. So I'm going to say, for our purposes, u of x, just to make our lives easier, is x to the fifth, because it doesn't matter. We're multiplying every term by either a positive or a negative, and it turns out to be the same. All right. Now I'm going to multiply this standard form by x to the fifth. So I get x to the fifth y prime plus 5x to the fourth y equals minus 3x to the eighth. This quantity is a derivative of what? X to the fifth y prime, right? If I take the derivative of this, I get this. And that equals minus 3x to the eighth. I'm going to integrate both sides. So x to the fifth y equals the integral of minus 3x to the eighth dx. And when you do this, when you multiply through by your integrating factor, you should, for what we're doing, you should always get an integral that's relatively easy to evaluate. That's part of the reason that we do that integrating factor. So I have x to the 5th y equals this integral minus x to the 9th over 3 plus c. Everybody good with that? I integrated correctly. And then we get y equals, I'm going to divide everything by x to the 5th, y equals minus x to the 4th over 3 plus c over x to the 5th. And our constant of integration would come from, that c would come from an initial condition on y or on y prime. Sometimes your initial condition is on the derivative. Isn't that nice? I think this step, to me, it's fun to see that, recognize that. And we also see that if we didn't include the c, didn't divide everything here by our x to the 5th, how much that would change our solution. Okay, questions? All right, tomorrow we will talk about a type of nonlinear differential equation that we can, by a nice little transformation, turn into a linear differential equation. Those are called Bernoulli equations. Bernoulli. And interestingly, the separable differential equations that we know how to solve already, so the one that I talked about before, dy dx equals x squared, you can apply this same technique to this equation. It makes it more complicated than just integrating, but it does work on these types of equations. Okay, all right.